Hi, this is Nick Bizai. This is another video in the series of hydraulics that we're doing. And today is pumping and horsepower. So I'm going to share this screen with you here. Bear with me. Pumping and horsepower. This is part one. This is, of course, a series of license exam training modules that we're putting together. This one being on hydraulics for distribution and plant operators. As we've mentioned in other hydraulic series that we're doing, water plants and distribution systems use math for hydraulic principles in a variety of ways. We have to use math to determine detention times, pressures, head-on pumps, elevated tanks. We have to determine velocities and flow rates of water moving through our system. Of course, we have to do the math to determine the amount of energy or horsepower that it takes for those pumps to move that water through our system. Also, many of these calculations are necessary to do other calculations, such as dosage control, our feed rates, our efficiencies of our systems, cost to operate our water plants and our distribution systems. So this is the basic math, part one, for pumping and horsepower. Now, a little bit of the terminology that we need to get out of the way first. Pumps basically are machines that we use to move water from a lower elevation to a higher elevation. It's simply what they are. In doing so, when we move that water to higher elevation, pumps provide us with the ability to move water through our system and our networks of pipes and storage facilities. We do that by putting pressure on the water. Pumps impart energy to the water. We call that pressure, or we call it head, feet in head in feet. Pumps move water through pipes in known volumes per unit of time. They provide flow rates. That was another video that we did on flow rates, and if you haven't seen that, you might want to go check that out so some of the terminology will make sense to you. Work done by pumps is calculated in units of horsepower, or HP. So work done by the pump creates horsepower by moving a volume of water per unit of time against a certain pressure and amount of flow rate. So let's look at the horsepower formula that we use that probably is familiar to most of you. It's a relationship between the amount of work that needs to be done to move water from the lower elevation to the higher elevation and the amount of time it takes to do this. So we're moving a quantity of water against a certain head and feet, and that formula is horsepower equal gallons per minute times the head and feet divided by 3960, which is a constant. Gallons per minute is the amount of water being pumped each minute. Of course, that water weighs something, and so the work is being done. The head and feet is the elevation to which the water is being pumped. Again, all divided by 3960. So some questions should occur to you at this point. How does that elevation that we're pumping against relate to pressure? Where does this number 3960 come from? And why is the act of work being done on water called horsepower in the first place? So to figure out all those answers to the question, we need to tell a little bit of story about the mankind's need for water and his ability to get it. So let's go back in time a little bit and look at the story. This is pumping background. Eons ago, millennia ago, human beings determined that it was more desirable to bring water to their place of residence than it was to go to the water each time you wanted to use it. Being able to do that allowed them ability to choose where they live. And if you think about it, thousands and countless numbers of times, early families probably moved near a pristine body of water that was flowing because the water would be available to them and all they needed to do was walk right over to it and get it. But when the spring rains came and flooded them out, wiped out all their possessions, they figured, we can't live here next to this stream. So they picked up what was left of their possessions and their family and they moved uphill. Of course, once they do that, there's a disadvantage. A lot of advantage to having that water brought to you, but those advantages come with difficulty. Number one, someone had to carry the water from the stream or well, and that was hard work because water is heavy. And that's the first thing we need to know about pumping. Water weighs 8.34 pounds per gallon. And if you figure all the number of gallons that a given person might use in a day, you can see how many trips would have to be made. Another thing is, someone had to construct a vessel or to contain or store that water at home because water takes up space. It's the second thing we need to know about pumping. Water has volume. In fact, every 7.4 gallons of it takes up 1 cubic feet of space. So if you think about all of the members of your family using several cubic feet of water in a given day, somehow that water has to be stored somewhere, preferably up in the air so it has pressure on it. It's a lot of space that has to be dedicated. Someone had to build a reservoir for it. And of course, once that water got from the stream, was carried up that 100 yards of hill up to that reservoir, someone had to actually lift it up into the storage vessel as fast or faster than it was being consumed. You know, while I'm carrying that water up and putting it in the tank, one of my little brothers or sisters is taking a shower, using that water up just as fast as I can carry it, because there's a rate of flow or Q, and we covered that in the previous video, so you should check that out. So all of that work required human energy, and eventually humans found other ways to do this, including using animals to do that work that humans used to do. Let's figure out how they managed that. It was determined that powerful draft horses of the day were best suited to carry the water to us. We used oxen, we used all kinds of animals. Draft horses seemed to be best. And we invented contraptions like water wheels, and this goes way back to the Romans. Water wheels that were literally a series of buckets mounted on a wheel. The power of the water going downstream would move the bucket in a circular motion. Buckets carried water up to the top, and we had it brought up to us. It was pretty nice. The problem with the water wheel, of course, is that it has to be located right next to the stream. We figured out that maybe if we could move the water wheel to the work that had to be done, other than just getting water from the stream, and if we could couple an animal to that, we could probably get the animal to do the work for us, making that water wheel much more portable for us, and that was important. So the best horses, of course, could work at a certain rate. With a set of pulleys, for example, a horse could lift up on average, and they figured this out, a weight of about 550 pounds through a distance of 1 foot in 1 second. Now, scientists of the day back in the 1600s, 1700s watched these animals work, quantified the amount of work they were doing, and set that to 550 pounds through that distance of 1 foot. We multiplied that times 60 seconds. On average, we see that a good draft horse, a standard good draft horse, could move 33,000 foot-pounds per minute of work being done. In other words, they could take a 33,000 pound weight, set on a pulley, and on average move it about a foot in 1 minute. Logically, we decided to call that 1 horsepower. If one good horse could move 33,000 pounds up in the air, and it took 1 minute to do that on average, over a series of examples that we looked at, logically we called that 1 horsepower. Eventually, a Scotsman by the name of James Watt came along and invented steam engines to do the work of horses. So we need to then figure out what's the relationship between horsepower and mechanical work being done. Let's talk about James Watt and the steam engine. We used the water wheel at the time, and I mentioned a little bit about that. For millennia, humans used the water wheel to do work such as lifting water. A wheel with buckets attached to place in a moving stream of water, and the flow turned the wheel and buckets in the water carried away at the high ground, as I mentioned. This worked very well for us, but was confined to the place of the flowing stream. It couldn't be used to do other work that we needed to be doing. Eventually, we learned to drive the wheel with the horses, as mentioned, and allowed the placement of the wheel anywhere it might need to be. An example, a flooded mine shaft. And this is where Watt comes into play. It fell then to Watt, who made improvements to an engine called the Newcomen engine, which used steam to do work, to make it feasible enough to drive that water wheel to replace the horse. We just use it with steam. He invented what's called a condenser to make that thing work efficiently. And as he began doing his work, he was called upon to bring his steam engine up to a mine that had flooded. They wanted to lift the water out of the mine shaft, and he applied his engine to that. And so through that kind of work and through some of the other experiments he was doing, he made some careful observations. He was able to compare the fuel consumption, which was the coal being burned to create the steam, and the amount of water lifted up from the mine, to the effort it would take for a horse to have done the same work. We knew that a horse could move 33,000 foot-pounds in a minute. That would be 1 horsepower. He looked at his machine that he made, his steam engine, coined the term horsepower, and he set it to comparing it against that 33,000 foot-pounds per second standard. And he made this computation here, very simple. He took the 33,000 foot-pounds, divided it by the fact that a gallon of water equals 8.34 pounds, moving it up the distance of 1 foot, that equaled a constant of 3,956.7. He rounded that number up to 3960, and we use it to this day. So therefore, Watt figured out that 1 horsepower is going to equal the gallons per minute that you have to move, which of course we know weighs something. If you do enough gallons per minute, you're going to move up to 33,000 33,000 foot-pounds of work. And you're going to come up and divide that by 3960, and you're going to figure out the horsepower of work being done. And later on, when people came around and started doing electrical experiments, and they developed machines that were run by electricity rather than the steam, they set the 1 horsepower that being done equal to about 746 watts of work being done. And they named that after the Scotsman, of course. 700. So that constant 1 horsepower equals 746 watts is what we use today. So let's remember some things that have to be come into play when we use this horsepower formula. The formula gallon per minute times the head divided by 3960 has some things that we have to follow. The horsepower calculations found on exams often require you to determine the flow rate. They don't give you the flow rate often, but typically they give it to you in some other terms, and you've got to get it down to gallons per minute. When you determine that rate of flow on your exam, you have to convert it to gallons per minute, and you can use the table at the end of this video, the last slide on this chapter, to determine how to get there from, say, 1 million gallons per day or cubic feet per second. That all has to be brought down to gallons per minute in order to use this formula. Another thing you got to remember is that the head in the formula has to be in total feet that the pump is working against. It may not give you total feet. They may give you pressure, and you'll have to convert it. Remember that total head may include friction losses and elevation difference, and we're going to cover that on part 2 of this video. This simple video here, initially part 1, does not include friction losses and elevation differences, that type of thing. We'll get into that more advanced topic in the next video. If you are given or you have calculated on your exam problem a pressure rather than head and feet, you must convert that pressure to feet of heads, excuse me, by multiplying by the constant 2.31. Of course, you can go to at the end of the chapter here to get that. So let's do a couple of simple problems. This is an example pump horsepower calculation where they're asking us if we're moving 500 gallons per minute against a head of 185 feet, what horsepower is required to do this work? I set my formula. And again, in the other slides, I'll stop here and mention, if you want to work this problem on your own, stop the video now, do the work, then start the video again for the right answer, because I'm scrolling up slowly. Okay, so I set the formula horsepower equals gallon per minute times the head divided by the 3960. Plug the numbers in, comes up to 500 gallon per minute times the 185 foot head divided by the 3960. And the horsepower I come up with is about 23.36 horsepower work being done. Here's another example, but on this one, they give you the pressure rather than the head, and you've got to do a quick conversion. Let's say they tell you that a well pump is moving 430 gallon per minute. The pressure gauge on the discharge pipe of that pump shows a reading of 35 PSI. What horsepower is this? And again, if you want to stop the video and do the problem, go ahead and give it a try. Remember, you got to convert the 35 PSI to feet of head. So I set the 35 PSI times 2.31 feet of head for every 1 PSI. That equals an elevation difference of 80.85 feet that I'm working against. That's what the 35 PSI equates to. But when I plug those numbers into my horsepower equation, I get 430 times 80.85 divided by 3960. It's about 8.8 horsepower, if my math is correct. Before we close out, let me give you a pump discussion that'll help set up the second video. The 2 previous horsepower calculations that I showed you are called theoretical horsepower problems. In reality, pumping is more complex than that. It's a task that involves more mathematics. That's what I'm going to get to on the second video. Those values that we just calculated show the theoretical amount of work that would need to be done to move that amount of gallons per minute, that much water, that much weight of water, if you want to put it that way, through that head distance that I gave you. But a pump is not a perfect machine. Some of the energy it develops is going to be lost to friction and other imperfections in the pump. In fact, if you work in a water plant, you go put your hand on a pump, you're going to feel warmth. That warmth is lost energy, not moving any water. It's lost in the form of heat. So in reality, more energy has to be put into that pump in order to get the work done. In addition to that, the motor that drives the pump is an imperfect machine too. You put your hand on a motor, you're going to feel heat. That heat is lost work. It's work that you're doing that is not going into moving that pump. So some energy is lost there also. And in fact, when you start moving water, you're going to encounter friction. Friction happens when water is moving through piping system as it moves faster and further. you're going to lose so much friction through the system that extra work has to be done to overcome it. So that's more energy that has to be lost. So when we do the part 2 of this video, we're going to discuss the practical end of pumping, all of the energy losses that have to be accounted for in order to do pump horsepower calculations. We'll address those in another video. Oh, went the wrong way. So one last slide here that I want to cover is the relationship between horsepower, the work being done, and the watt. W-A-T-T, named after James Watt. It's an amount of work that scientists discovered when they were doing their energy experiments. And they came up with a word that they needed to use to describe the amount of work being done. We already discussed the work that it took to move 33,000 pounds of water through a distance of 1 foot in 1 minute. We called that 1 horsepower. Well, in their electrical studies of our electrical forces and also electromagnetism and gravity, scientists decided to coin the term watt to describe an amount of energy transferred in unit time. They determined that 1 horsepower would be equal to 746 watts, or 0.746 kilowatts. And you can find that at the end, the table at the end of this chapter. So therefore, a 1 horsepower system running for 1 hour would consume 0.746 kilowatt hours. And that's where kilowatt hours comes from. If you knew how much your electrical utility was charging you for kilowatt hours, you multiply it, those cents, say 15 cents times the 0.746 times the number of hours that you run, you can figure out how much it costs to run your pump. But we'll get into all that on our next video. There's the table that I put at the end of all of the chapters for hydraulics, conversion factors that you can use. And with that, I'm going to close the video out. And we'll be finished with this. Thank you for tuning in, and we'll get this done.